Hello there, and welcome to Math for Sleep. I'm really glad you found your way here tonight. Maybe you're already tucked into bed, the covers pulled up soft around your shoulders. Or maybe you're just beginning to settle in after a long day. Maybe your room is dark, or perhaps there's a dim light somewhere casting gentle shadows on the walls. However you've arrived at this moment, you're welcome here. This is a space where mathematics becomes something quiet, something to wander through as you drift towards sleep. Tonight, we're going to explore one of the strangest, most beautiful questions that mathematics has ever asked. Can infinity be bigger than infinity? It sounds like a contradiction, doesn't it? Like asking if endlessness can be more endless than endless. And yet, what we'll discover together, slowly and without any rush, is that infinity isn't one thing, it's many things. An entire landscape of infinities, each one larger than the last, stretching out in ways that seem impossible until you look at them from just the right angle. You don't have to understand everything you hear tonight. That's not what this is for. This is for rest, for letting your mind settle into ideas the way you might settle into a comfortable chair. If you fall asleep halfway through, that's perfect. If you drift in and out, catching fragments of thoughts about numbers and patterns, that's exactly right. There's no test at the end, no quiz, just mathematics told softly, like a bedtime story. Because that's what it is. A story about infinity, about a mathematician who dared to ask impossible questions about the ways that endless things can surprise us. Before we begin our slow journey into these infinite landscapes, if you find these gentle explorations help you unwind at the end of your day, consider giving this video a like and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time, looking for something calm and curious to ease them towards sleep. And now, let's begin. Let's drift slowly into the question of whether infinity can be bigger than infinity, and discover together what mathematics has to say about the endless. Let's start with something simple, or at least something that seems simple at first. What is infinity? You've heard the word before. Maybe you've seen the symbol, that sideways figure 8, the one that loops back on itself forever. Maybe you've thought about infinity when looking up at the stars at night, wondering if the universe goes on and on without end. Maybe you've heard someone say, "I love you, infinity," or "I'll be your friend for infinity years." It's one of those words that feels like it should mean something obvious. Endless, forever, without limit, without boundary, without end. But when you try to really think about infinity, when you try to pin it down, it starts to feel slippery. Like trying to hold water in your hands, it runs through your fingers. What does it actually mean for something to be infinite? Does it mean you could count it forever and never finish? Does it mean there's no last one? Or is it something else, something harder to grasp? Most of what we experience in daily life is finite. Your room has walls, a book has a last page, a year has a last day. Even very large things that seem almost infinite in their vastness, eventually have edges. The grains of sand on all the beaches in the world, it's a huge number, almost impossible to imagine, but it's still a number. You could, in theory, count them. It would take longer than anyone has ever lived, longer than civilizations have existed, but eventually, hypothetically, you'd reach the last grain and be done. But infinity isn't like that. infinity doesn't have a last one. If you started counting 1, 2, 3, 4, going on and on, you would never reach infinity. You could count for 1,000,000 years, for 1,000,000,000 years, for as long as the universe has existed, and you'd still be no closer to infinity than when you started. Because infinity isn't a destination you're traveling toward. It's not a really big number sitting out there waiting for you to finally arrive. It's something else. It's the quality of never stopping, the property of endlessness itself. Think about the whole numbers for a moment. 1, 2, 3, 4, and so on, going up forever. We call these the natural numbers, the counting numbers, the ones children learn first. How many of them are there? Well, there's no largest one. If you think of a big number, any big number, a trillion, a Google, a number with so many zeros, it would fill this entire script. I can always add one to it. I can always find a bigger one. So the natural numbers are infinite. They go on forever. That much seems clear. But here's where it starts to get strange. Here's where the question begins to unfold. Are the even numbers infinite? Of course they are. 2, 4, 6, 8, going up without end. You can always find another even number. Just keep adding 2. But wait, there's something curious here. The even numbers are a part of the natural numbers. They're a subset, as mathematicians would say. Half of the natural numbers are even, and half are odd. So there should be fewer even numbers than natural numbers, right? That's how it works with finite sets. If you have 10 apples and 5 of them are red, there are fewer red apples than total apples. But infinity doesn't follow the same rules. And this is where we begin to see that infinity is strange, that it behaves in ways that don't match our everyday intuition. You don't have to solve this puzzle right now. You don't have to understand it fully. Just let the question sit there, gently, like a smooth stone you are holding. Can something infinite be smaller than something else that's also infinite? Can there be, in some sense, more natural numbers than even numbers, even though both go on forever? Maybe your eyes are growing heavy. Maybe your thoughts are starting to blur at the edges. That's fine. That's more than fine. The mathematics will still be here, patient and quiet, whether you're listening or not. These questions about infinity have been waiting for thousands of years. They can wait through the night while you sleep. And when you wake, if you remember any of this, it might just be a soft impression, a feeling that infinity is more complicated than you thought, more interesting, more full of surprises. And that's enough. The human mind wasn't really built to think about infinity. We evolved to deal with finite things. How many predators are in the bushes? How many berries are on the tree? How many days until winter? Our brains are good at counting things we can see, things we can touch, things that have edges and boundaries. But infinity? Infinity is beyond the edge of experience. It's a mathematical concept, an abstraction, something we approach with symbols and logic rather than with our senses. And yet, we're drawn to it. Something about infinity captures the imagination. Children ask about it. Where does space end? What's beyond the edge of the universe? If you keep counting, do you ever stop? These aren't foolish questions. They're profound ones. They're the same questions that mathematicians have grappled with for centuries. And some of those mathematicians discovered things about infinity that seemed, at first, impossible. things that made other mathematicians angry, that caused arguments and controversy, that challenged everything people thought they knew about numbers. One man in particular, a mathematician named Georg Cantor, asked questions about infinity that nobody had quite asked before. And the answers he found, the discoveries he made, changed mathematics forever. He showed that infinity isn't just one thing. He showed that there are different sizes of infinity, that some infinities are, in a very precise and provable way, bigger than others. And that discovery, as beautiful as it was, also brought him great suffering. His ideas were rejected. He was mocked and ridiculed by other mathematicians. And the struggle to defend his work, combined with other factors in his life, took a terrible toll on his mental health. But we're getting ahead of ourselves. We'll come to Georg Cantor soon, and we'll walk gently through his story, through his discoveries, through his struggles. For now, just rest with the question: can infinity be bigger than infinity? Let it float there in your mind, not demanding an answer, just existing as a curiosity, something to wonder about, something strange and beautiful and impossible sounding. You're lying there, maybe on your back, maybe on your side, feeling the weight of your body against the bed. Your breathing is slow or getting slower. The sounds of the day are fading. And somewhere in the quiet, there's this question about infinity, about endless things, about whether one kind of forever can be larger than another kind of forever. It doesn't make sense. Not yet, but it will. Slowly, gently. As we wander through these ideas together, it will begin to make a kind of sense that's different from everyday sense. A mathematical sense, a sense that has its own strange logic, its own peculiar beauty. We could talk about how ancient philosophers thought about infinity, how they argued about whether it could exist at all. Aristotle believed that infinity was only potential, never actual. You could always count one more number, but you could never have an actually infinite collection of things. Other thinkers disagreed. They said infinity must exist, must be real in some sense, or else mathematics couldn't work the way it does. These debates went on for centuries, back and forth, never quite resolved. And then, in the late 1800s, Georg Cantor came along and did something remarkable. He didn't just argue about whether infinity existed. He didn't just philosophize about it. He built a mathematics of infinity. He created tools, concepts, theorems that let him compare infinite sets, that let him prove things about them with the same rigor that mathematicians use to prove things about finite numbers. And what he proved was stunning. What he proved was that infinity comes in different sizes. But let's not rush. Let's take our time. There's no hurry here. The night is long and sleep is patient, and mathematics, especially mathematics about the infinite, deserves to be approached slowly. Let's drift for a moment. Let's breathe. Let's let the question just be a question. Can infinity be bigger than infinity? We'll find the answer, bit by bit, thought by thought, in a way that feels less like learning and more like discovering something you almost knew already, something that was waiting there, quiet and true, all along. Before we go deeper into the mathematics of infinity, let's talk about the man who discovered it. Not because you need to know his biography to understand his ideas, but because sometimes knowing the person behind the mathematics makes the ideas feel more human, more real. And Georg Cantor was very human. He was brilliant and troubled, visionary and vulnerable, someone who saw things no one else could see and paid a price for that vision. Georg Ferdinand Ludwig Philipp Cantor was born on March 3, 1845, in St. Petersburg, Russia. His father was a Danish merchant who had moved to Russia for business, and his mother was Russian and Roman Catholic. They were a cultured family, artistic, musical. Georg's mother was from a family of musicians, and that artistic sensibility ran through young Georg as well. He became an accomplished violinist, someone who could have pursued music professionally if he'd chosen that path. But Georg's gifts were mathematical. From a young age, he showed an unusual talent for numbers, for patterns, for logical thinking. His teachers noticed it. His father noticed it. And when Georg was 11 years old, the family moved to Germany because of his father's failing health. Georg continued his education there, excelling especially in mathematics, particularly in trigonometry, which seemed to come naturally to him. There was some tension, though, between what Georg wanted and what his father wanted for him. His father was a practical man, a businessman, and he wanted Georg to become an engineer, something solid, something with clear economic prospects. But Georg wanted to study pure mathematics. He wanted to explore numbers not for what they could build or calculate, but for their own sake, for the beauty of mathematical truth itself. Eventually, Georg convinced his father to let him pursue mathematics. He went to study at the University of Zurich and later at the University of Berlin, where he learned from some of the greatest mathematicians of the time. Karl Weierstrass, who revolutionized mathematical analysis, Ernst Eduard Kummer, who worked on number theory, and Leopold Kronecker, a powerful mathematician who believed that mathematics should be strictly finite, that only things you could construct in a finite number of steps from the natural numbers were truly meaningful mathematically. This last teacher, Kronecker, would later become one of Cantor's fiercest opponents. Cantor received his doctorate in 1867, writing a dissertation on number theory. He then got a position at the University of Halle, a respectable but not prestigious university. Halle would remain his academic home for his entire career, much to his disappointment. He wanted a position at a major university, particularly at Berlin, which was the center of the mathematical world in Germany at that time. But he never got it. His ideas were too controversial, and Kronecker's opposition made sure that the doors to Berlin remained closed to him. In 1874, Cantor married Vally Gutmann, a friend of his sister. They had 6 children together. By all accounts, he was a devoted husband and father, someone who loved his family, who played violin for them, who tried to provide for them even though his salary was modest. He was not a wealthy man. The estate from his father helped, but life was not luxurious. And beneath the surface of domestic life, there was always the mathematics, the questions about infinity that he couldn't stop thinking about. It was during the 1870s that Cantor began his revolutionary work on set theory and infinite numbers. He started by trying to solve a technical problem about trigonometric series, about whether certain mathematical functions could be represented in unique ways. This led him to think carefully about sets of points on a line, about what it meant for 2 sets to be the same size, about how to compare infinite collections. And the deeper he went, the stranger things became. In 1874, Cantor published a paper that contained a shocking result. He proved that the set of real numbers, all the points on a number line, could not be put into a one-to-one correspondence with the natural numbers. In other words, the real numbers were a bigger infinity than the counting numbers. This was the first time anyone had proved rigorously that there were different sizes of infinity. Before Cantor, mathematicians either avoided talking about infinity as a completed thing, or they assumed that all infinities were somehow the same. Cantor showed they were wrong. The paper was submitted to Crell's Journal, a prestigious mathematical journal. But one of the referees was Kronecker, and Kronecker did not like what he saw. He thought Cantor's ideas were dangerous, meaningless, that treating infinite sets as actual completed objects was a kind of mathematical heresy. He tried to block the publication. It was only through the intervention of another mathematician, Richard Dedekind, who was a friend and supporter of Cantor, that the paper eventually appeared. This was just the beginning of the opposition Cantor would face. Over the next decade, he published more papers developing his theory of transfinite numbers, showing that there was an entire hierarchy of infinities, each one larger than the last. He introduced new notations, the Aleph numbers, symbols to represent the different sizes of infinite sets. He proved theorems that seemed paradoxical, that challenged intuition at every turn. And with each publication, the criticism grew louder. Kronecker was the most vocal opponent. He called Cantor a scientific charlatan, a corrupter of youth, a renegade. These weren't just academic disagreements. They were personal attacks meant to damage Cantor's reputation, to prevent his ideas from spreading. And they worked to some extent. Many mathematicians were reluctant to embrace Cantor's work. Some thought it was too abstract, too far removed from the concrete world of numbers and calculations. Others simply didn't understand it. And some, like Kronecker, thought it was fundamentally wrong, that it would lead mathematics into contradiction and confusion. Cantor felt the weight of this opposition deeply. In 1884, he suffered his first major bout of depression. It was severe enough that he couldn't work, couldn't think about mathematics, could barely do anything except go through the motions of his teaching duties. He wrote to a colleague, "I don't know when I shall return to the continuation of my scientific work. At the moment, I can do absolutely nothing with it and limit myself to the most necessary duty of my lectures. How much happier I would be to be scientifically active if only I had the necessary mental freshness." For a long time, historians thought that Cantor's mental illness was caused by the stress of the opposition to his work, by Kronecker's attacks, by the failure to prove the continuum hypothesis, a conjecture about infinity that Cantor believed was true but couldn't prove. But more recent scholarship suggests that Cantor likely suffered from what we would now call bipolar disorder or manic depression, a biological condition that would have afflicted him regardless of his professional struggles. The opposition didn't cause his illness, but it certainly didn't help. It made everything harder. After that first breakdown, Cantor tried to recover. He took time away from mathematics. He became interested in philosophy, in theology, in questions about the relationship between his mathematical infinities and the theological concept of God's infinity. He even developed a theory that Francis Bacon was the true author of Shakespeare's plays, publishing pamphlets about it. These were distractions, ways to give his mind something to focus on besides the mathematics that had brought him so much pain. But he did continue to work on set theory, on and off, for the rest of his life. In the 1890s, he published more papers, refining his ideas, responding to critics, trying to build a solid foundation for his theory. Some mathematicians were starting to come around. Bertrand Russell saw the brilliance in Cantor's work. David Hilbert, one of the greatest mathematicians of the early 20th century, famously said that Cantor had created a paradise from which mathematicians would never be expelled. But the praise came late, and it came alongside continued controversy and confusion about the implications of Cantor's ideas. Cantor's mental health continued to deteriorate over the years. He spent time in sanatoriums under professional care, trying to manage his depression and other symptoms. He did continue to teach when he could, and he remained involved in the mathematical community, attending conferences, corresponding with other mathematicians. But the periods of productivity became shorter, the periods of illness longer. In 1913, he retired from teaching. By then, he was in poor health, both mentally and physically. World War I brought additional hardships, food shortages, the general chaos and suffering of the war years. In December 1917, Cantor was admitted to a sanatorium in Halle, much against his will. He wrote letters to his wife begging to be allowed to come home, but he never did. On January 6, 1918, Georg Cantor died of a heart attack in that sanatorium. He was 72 years old. It's a sad ending to a remarkable life. A man who saw truths that others couldn't see, who built a new branch of mathematics from almost nothing, who asked questions nobody had asked before and found answers nobody had imagined. And yet he suffered greatly for it. He was mocked, rejected, misunderstood. His work was called nonsense, disease, corruption. He struggled with mental illness in an era when there was little understanding and less effective treatment. He died in an institution, far from his family, in the midst of a war, his final years clouded by illness and isolation. And yet, his ideas survived. His ideas thrived. Within a few decades of his death, Cantor's set theory had become a cornerstone of modern mathematics. The infinities he discovered, the proofs he constructed, the concepts he invented, all of it became standard material in university courses, foundational to entire fields of mathematics. The paradise that Hilbert spoke of, the one Cantor created, it turned out to be real. Mathematicians never were expelled from it. If anything, they built more and more upon the foundations Cantor laid. So when we talk about infinity, about whether infinity can be bigger than infinity, we're walking in Georg Cantor's footsteps. We're exploring the landscape he mapped out, often alone, often in pain, but with a vision clear enough to see truths that had been hidden since numbers were first counted. It seems important to remember that mathematics is done by people, by human beings, with all their brilliance and all their fragility. And sometimes the most beautiful mathematics comes at the highest cost. Maybe you're still awake. Maybe you've drifted off and come back. Either way is fine. The story of Georg Cantor is told now, gently, the way you might tell any story at night, with care for the person at the center of it, with recognition that he was someone who struggled and created and suffered and gave the world something profound. Now we can move forward into his mathematics, into the ideas he discovered. knowing a little bit about the person who found them. Before we dive into countable infinity, let's take a moment to think about numbers themselves. What are numbers really? It's such a basic question that we rarely ask it. We learn to count as children. 1, 2, 3. We learn to add and subtract, multiply and divide. Numbers become tools, things we use, practical objects for measuring and calculating. But what are they fundamentally? Are numbers real things that exist somewhere? Or are they concepts, ideas that exist only in minds? When you think of the number 5, what are you thinking of? Not 5 objects, just 5 itself. The pure idea of fiveness, separate from any particular collection of 5 things. That abstraction, that pure number, where does it live? In your brain, in some platonic realm of forms, or nowhere at all? These are ancient questions. Philosophers and mathematicians have argued about them for thousands of years, and infinity makes these questions even more puzzling, because at least with small numbers, we have direct experience. You can hold 5 pebbles in your hand. You can see 5 stars. You can count 5 days. But infinity? You've never experienced infinity directly. You've never counted to it, never held it, never seen it complete. So when mathematicians reason about infinity, when they prove theorems about it, what exactly are they doing? Cantor's approach was to treat infinite sets as mathematical objects that could be studied rigorously. He didn't worry too much about whether they really existed in some metaphysical sense. He cared about whether you could define them precisely, whether you could reason about them logically, whether you could prove things about them, and he showed that you could. The infinite, he demonstrated, was not beyond mathematics. It was part of mathematics, subject to the same standards of rigor and proof as everything else. This was revolutionary. Before Cantor, many mathematicians were uncomfortable with the idea of completed infinity. They preferred to think of infinity as potential, never actual. You could always count one more, but you could never have a completed infinite collection. Aristotle had argued for this view, and it dominated thinking about infinity for centuries. The infinite was a process, not an object, a becoming, not a being. But Cantor said no. You could treat an infinite set as a completed whole, the set of all natural numbers, 1, 2, 3, and so on. That's a thing. It's an infinite thing, but it's still a thing. You can talk about it, reason about it, compare it to other infinite sets. And by doing this, by treating the infinite as actual rather than merely potential, Cantor opened up a whole new realm of mathematics. Of course, this raised questions. If you can talk about the set of all natural numbers, can you talk about the set of all sets? What about the set of all things that are not members of themselves? These questions led to paradoxes, contradictions that showed that you had to be careful about which sets you allowed yourself to discuss. The foundations of set theory had to be worked out carefully, with precise axioms that avoided contradiction. And that work, carried out by mathematicians and logicians in the early 20th century, resulted in the framework we use today, called Zermelo-Fraenkel set theory, often with the axiom of choice added, abbreviated ZFC. Within that framework, Cantor's infinities make perfect sense. They're well-defined, consistent, provable, but the framework itself is a choice, a particular way of setting up the rules of mathematics. And as we've seen with the continuum hypothesis, some questions remain open even within that framework. The axioms don't determine everything. there's still room for mystery, for multiple possibilities, for questions that resist definitive answers. Maybe numbers are like that too. Maybe the question, "What are numbers?" doesn't have a single answer. Maybe different frameworks, different philosophies, different ways of thinking about mathematics all capture something true about numbers without exhausting their nature. Numbers are useful tools. They're abstract patterns. They're relationships between quantities. They're formal symbols manipulated according to rules. They're objects in a Platonic realm. They're all of these things, or none of them, depending on how you look. What matters for our purposes tonight is that numbers, including infinite numbers, can be studied mathematically. We can make precise statements about them. We can prove theorems. We can compare them. And when we do, we discover surprising things. Like the fact that infinity is not uniform, not monolithic. It has structure, variety, levels. Some infinite sets are larger than others in a precise, provable sense. And that's what we're here to explore. You're still with me, or you're drifting, or you've fallen asleep and come back, and all of those are fine. The mathematics doesn't demand your constant attention. It's patient, it waits. And if you lose the thread, if your mind wanders or sleep pulls you away, that's not a failure. That's the whole point. Mathematics as a companion to rest, not as a task to complete. Ideas to float through rather than problems to solve. Let's begin with the simplest infinite set, the one Cantor used as his starting point. The natural numbers, 1, 2, 3, 4, 5, and so on, going up forever. How many natural numbers are there? The answer, in a sense, is infinity. But Cantor wanted to be more precise than that. He wanted a way to measure the size of an infinite set, a way to compare one infinite set with another. And the tool he developed was beautifully simple. It was called one-to-one correspondence. Here's the idea. If you want to know if two sets are the same size, you try to match them up. You pair each element in the first set with exactly one element in the second set, with nothing left over on either side. If you can do that, if you can create this perfect pairing, then the two sets have the same size, the same cardinality, as mathematicians say. This works for finite sets. If you have 5 apples and 5 oranges, you can pair them up perfectly. 1 apple with 1 orange until they're all matched. So the set of apples and the set of oranges have the same cardinality. They're both size 5. But Cantor realized this idea could work for infinite sets too. You could try to create a one-to-one correspondence between two infinite sets. And if you succeeded, you could say they were the same size, even if both were infinite. And if you tried to create a correspondence and found that you couldn't, that no matter how clever you were, there would always be elements left over in one set, then you could say that one set was bigger than the other. So let's start with the natural numbers. 1, 2, 3, 4, and so on. This is the first infinite set, the simplest one, the one we're most familiar with. Cantor decided to use this set as his standard, his measuring stick for infinity. He called the size of the natural numbers Aleph Null, written with the Hebrew letter Aleph and a subscript 0. Aleph Null is the smallest infinite cardinal number. It's the size of the set of counting numbers. Now, any set that can be put into one-to-one correspondence with the natural numbers is said to be countably infinite. The word countable here doesn't mean you could actually count all the elements, finish the job in any amount of time. It means you could, in principle, assign each element a natural number, 1, 2, 3, and so on, in such a way that every element gets a unique number and every number gets assigned to an element. You'd never finish, but there's a systematic way to proceed, a pattern that would, if continued forever, cover everything. So the natural numbers themselves are countably infinite. That's sort of obvious. They define what countable means. But what about other sets? Let's look at some examples. And this is where things start to get interesting, where infinity begins to show its strange nature. Consider the even numbers, 2, 4, 6, 8, and so on. Are the even numbers countably infinite? At first glance, you might think, well, there are fewer even numbers than natural numbers because the evens are only half of the naturals. So maybe they're a smaller infinity. But let's try to create a one-to-one correspondence. Let's try to match up every natural number with a unique even number. It's easy. Match 1 with 2. Match 2 with 4. Match 3 with 6. In general, match the natural number n with the even number 2n. If you do this, every natural number gets paired with exactly one even number, and every even number gets paired with exactly one natural number. The correspondence is perfect. Nothing is left out. So the even numbers, despite seeming like half of the natural numbers, are actually the same size as the natural numbers. They're both Aleph null. They're both countably infinite. This is one of the first strange things about infinity. A proper subset, a part of something, can be the same size as the whole. With finite sets, that's impossible. If you have 10 apples and you take away half of them, you have fewer apples. But with infinite sets, you can remove half the elements and still have the same size set. The part can equal the whole. It's counterintuitive, but it's provably true. Let's try another one. What about the integers? That's all the natural numbers, plus 0, plus all the negative numbers. So -3, -2, -1, 0, 1, 2, 3, and so on in both directions. This set seems bigger than just the natural numbers because it includes everything the natural numbers do, plus a whole infinite set of negatives. So surely the integers are a larger infinity than the natural numbers. But no, we can create a one-to-one correspondence here too. It takes a little more thought, but it's possible. Start with 0 and match it to 1. Then go to +1 and match it to 2. Then -1 and match it to 3. Then +2 and match it to 4. Then -2 and match it to 5. Keep alternating back and forth between positive and negative. If you do this, you'll eventually hit every integer, and every integer will get matched to exactly one natural number. So the integers are countably infinite, same size as the natural numbers. Aleph null again. Even more surprising, the rational numbers, all the fractions, all the numbers that can be written as one integer divided by another, are also countably infinite. This is really shocking. Between any two fractions, you can find infinitely many more fractions. They're densely packed along the number line. And yet, Cantor showed that you can still list them in a systematic way that eventually hits every single rational number. The technique involves a clever diagonal argument, where you arrange all possible fractions in a grid and then zigzag through the grid, skipping duplicates. It's beautiful and intricate, and the result is that the rationals, dense as they are are still only countably infinite. So we have these examples: natural numbers, even numbers, integers, rational numbers, all countably infinite, all the same size, all aleph null. It starts to seem like maybe all infinite sets are the same size. Maybe countable infinity is the only infinity there is. This was what most mathematicians before Cantor assumed. Infinity was infinity. There was no distinction. But Cantor was about to show them they were wrong. Before we get there, let's pause and think about a wonderful thought experiment that illustrates countable infinity in a playful way. It's called Hilbert's Hotel, named after the mathematician David Hilbert, though the idea is closely related to Cantor's work. Imagine a hotel with infinitely many rooms, numbered 1, 2, 3, and so on, going on forever. And imagine that every single room is occupied. A guest in room 1, a guest in room 2, a guest in every room, all the way out to infinity. Now a new guest arrives at the front desk. They want a room. The manager looks at the reservations and sees that every room is full. In a normal, finite hotel, this would be the end of the story. Sorry, no vacancy. But this is Hilbert's Hotel, an infinite hotel, and the manager has a clever solution. She asks the guest in room 1 to move to room 2. She asks the guest in room 2 to move to room 3. She asks every guest to move to the next room. Everyone shifts over by one. What happens? Every guest still has a room. Nobody gets left out in the hallway because there's no last room. There's always a next room for everyone to move into. And now, room 1 is empty. The new guest can check in. The hotel had no vacancy. It was completely full. And yet it was able to accommodate one more guest because it's infinite. But wait, it gets better. What if an infinite bus arrives at Hilbert's Hotel carrying infinitely many new guests? Surely now there's a problem. The hotel is already full, and now there's an infinite number of people who need rooms. How could that possibly work? The manager has another clever solution. She asks the guest in room 1 to move to room 2. She asks the guest in room 2 to move to room 4. She asks the guest in room 3 to move to room 6. Every existing guest moves to a room number that's double their current room number. So the guest in room N moves to room 2N. What does this accomplish? Well, all the existing guests are now in even-numbered rooms, 2, 4, 6, 8, and so on. And that means all the odd-numbered rooms are empty, 1, 3, 5, 7, and so on. And there are infinitely many odd numbers. So there are infinitely many empty rooms. The infinite busload of new guests can all check in. Each one gets an odd-numbered room, and everyone has a place to stay. This is the strange arithmetic of countable infinity. Full plus 1 equals full. Full plus infinity equals full. Because there's always room to shift things around, always room to rearrange, always a next space available. It doesn't make sense with finite quantities, but with infinity, it works perfectly. Hilbert's Hotel is a paradox, but it's a veridical paradox, meaning it's not actually a contradiction. It's just deeply counterintuitive. It challenges our expectations, but it's logically consistent. And it helps us see what countable infinity really means. It means you can enumerate things, assign them numbers, even if you can never finish the enumeration. It means you can always fit one more, or infinitely many more, because there's no last spot to run out of. The key insight here is that countable infinity has a structure. It has a pattern. You can organize it, list it, systematize it, even though you can never complete it. And that structure, that ability to correspond with the natural numbers, is what makes it countable. It's the smallest kind of infinity, the most orderly kind, the one closest to our intuitions about counting. But not all infinities are like this. Not all infinite sets can be put into one-to-one correspondence with the natural numbers. And that's where things get really interesting. That's where Cantor made his most revolutionary discovery. That's where we find infinities bigger than countable infinity. Infinities that can't be listed no matter how clever you are. Infinities that resist enumeration. But we're taking our time. We're not rushing. Maybe you're feeling the pull of sleep now, the gentle weight of drowsiness settling over you. That's good. That's exactly right. Let the ideas wash over you. Countable infinity. Aleph Null. Hilbert's Hotel. One-to-one correspondence. These concepts will be here when you wake. They've been here for more than a century, waiting patiently. They can wait through the night while you rest. And when we return, when we continue this journey, we'll discover what lies beyond countable infinity. We'll find the infinities that are bigger, the ones that Cantor discovered, the ones that showed the true depth and richness of the infinite. The world of countable infinity is vast and surprising. It includes the natural numbers, the integers, the rational numbers. It includes many sets that at first glance seem much larger than the natural numbers, but turn out to have the same cardinality. This is the realm of Aleph Null, the first infinite cardinal, the smallest infinity. It's a strange and wonderful place where half can equal the whole, where infinity plus infinity equals infinity, where full can always accommodate more. But it's not the only infinity. And discovering that fact, proving that there were larger infinities, was perhaps Cantor's greatest achievement. Because it's one thing to say, I think there might be bigger infinities. It's another thing entirely to prove it rigorously, to demonstrate with mathematical certainty that some infinite sets simply cannot be put into correspondence with the natural numbers, that they're fundamentally larger, uncountable. That proof, when it came, changed everything. It showed that the landscape of infinity was richer than anyone had imagined. It opened up questions that are still being explored today, and it established Cantor as one of the great mathematical minds of his era, even as it brought him controversy and opposition. We're about to see how he did it, how he proved that some infinities are bigger than others. And the argument he used is so elegant, so beautiful, so clever, that it's worth taking our time with, letting each step unfold naturally, appreciating the logic of it. But first, let's think for a moment about the real numbers themselves. What are they? And why might we suspect they're different from the rationals? When you imagine a number line, a line stretching left and right forever, with zero in the middle, what you're imagining is filled with real numbers. Every point on that line corresponds to a real number, and every real number corresponds to a point. The line is continuous, unbroken, no gaps anywhere. Between any 2 points, no matter how close, there are infinitely many more points. Now, we've already said that the rational numbers, or the fractions, are countably infinite, and the rational numbers are dense on the number line. Between any two rationals, you can find another rational. In fact, you can find infinitely many rationals. They're everywhere, packed infinitely tightly. So you might think, well, If the rationals are dense and they're countable, maybe they fill the whole line. Maybe every point is a rational number. But that's not true. The ancient Greeks discovered this. They found that the square root of 2, the length of the diagonal of a square with sides of length 1, cannot be written as a fraction. It's not rational. There's no pair of whole numbers whose ratio equals exactly the square root of 2. You can get close. You can find fractions that approximate it very closely, but you can never get it exactly. The square root of 2 is irrational. This troubled the Greeks deeply. They had built their mathematics largely on whole numbers and rationals. The discovery that some lengths couldn't be expressed as ratios of whole numbers was shocking, almost scandalous. Legend has it that the Pythagoreans, a mathematical cult of sorts, tried to keep the discovery secret. And when one member, Hippasus, revealed it publicly, they allegedly threw him overboard from a ship and drowned him. Whether that story is true or not, it captures the sense of crisis that the discovery of irrational numbers caused. But irrational numbers are real in a very concrete sense. They show up in geometry, in measurements, in nature. The square root of 2 exists. You can construct it. You can measure it. It's just not rational. It's something else, something that doesn't fit into the neat framework of fractions. And there are more irrational numbers, many more. Pi, the ratio of a circle's circumference to its diameter. That's irrational. Its decimal expansion goes on forever without repeating. E, the base of natural logarithms, the number that shows up in calculus and growth processes and compound interest. That's irrational too. The golden ratio, that special proportion that appears in art and architecture and plants and shells. Irrational. The square root of any non-perfect square number. Irrational. In fact, almost all real numbers are irrational. If you pick a random point on the number line, the probability that it's a rational number is 0. Not because there are no rationals. There are infinitely many rationals, as we've seen, but they're somehow sparse compared to the totality of all real numbers. The irrationals fill the gaps between the rationals, and those gaps turn out to be where almost everything is. This is hard to visualize. The rationals are dense. They're everywhere. Between any two rationals, infinitely many more. And yet, they're not enough to fill the line. The irrationals are needed. And when you add them, when you include all the numbers that can't be written as fractions, you get the real numbers, the complete number line, the continuum. Are the real numbers countable? Can you list them, enumerate them, the way you can list the rationals? At first, it seems like maybe you can. After all, the rationals are dense, and we listed them. Maybe the reals, even with the irrationals added, can still be listed in some clever way. Maybe there's a pattern, a system that would let you eventually hit every real number if you just keep going long enough. Cantor proved that the answer is no. The real numbers are uncountable. There are too many of them to ever put into a list, even an infinite list. They resist enumeration. They're a bigger infinity. And the proof of this is what we're about to explore. It's called the diagonal argument, and it's one of the most famous and beautiful proofs in all of mathematics. Maybe you're getting sleepier, the idea's starting to blur. That's fine. Stay with it a little longer if you can. The diagonal argument is worth seeing, worth understanding, even in a fuzzy, half-asleep way. Because it's not just a proof, It's a glimpse into how mathematics works at its deepest level. How you can prove something exists by showing that assuming it doesn't exist leads to a contradiction. How you can demonstrate the uncountable by trying to count it and showing that the attempt must fail. It's elegant, it's beautiful, and it's about to show us that infinity is bigger than we thought. Now we come to one of the most beautiful, most elegant proofs in all of mathematics. It's called Cantor's diagonal argument, and it shows something that seems impossible. It shows that the real numbers, all the points on a number line, cannot be put into one-to-one correspondence with the natural numbers. The real numbers form a larger infinity. They are uncountably infinite. Let's take this slowly, because it's worth understanding, and because the proof itself is so clever, so surprising, that it deserves to be appreciated. We're going to show that there are more real numbers than natural numbers, even though both are infinite. And we're going to do it by assuming the opposite and then showing that the assumption leads to a contradiction. First, what are the real numbers? They're all the numbers you can think of. All the natural numbers, 1, 2, 3. All the integers, including negatives, and 0. All the fractions, the rational numbers, but also all the numbers in between, the irrational numbers, the ones that can't be written as fractions. Numbers like the square root of 2, which the ancient Greeks discovered and which troubled them deeply because it couldn't be expressed as a ratio of whole numbers. Numbers like pi, the ratio of a circle's circumference to its diameter, which goes on forever, with no repeating pattern. Numbers like e, the base of natural logarithms, which shows up in growth and decay processes throughout nature and mathematics. The real numbers fill the number line completely. Between any two real numbers, no matter how close together they are, there are infinitely many more real numbers. They're continuous, a continuum, hence the name of the continuum hypothesis, which we'll get to later. For now, just understand that the real numbers are dense, infinitely dense, in a way that the rationals are dense, but somehow more so, because the irrationals fill in all the gaps the rationals leave. Cantor wanted to know, are the real numbers countably infinite? Can you create a list, a systematic enumeration that eventually includes every real number, the way you can create a list that includes every rational number? To make the problem more manageable, he focused on just the real numbers between 0 and 1. All the decimals, from 0 to 0.9999. If you can show that even this subset of the real numbers is uncountable, then certainly all the real numbers are uncountable too. So here's the question. Is there a one-to-one correspondence between the natural numbers and the real numbers between 0 and 1? Can you list all those decimal numbers in a sequence, first, second, third, and so on, such that every decimal eventually appears somewhere in the list? Cantor said no. And here's how he proved it. He said, suppose you think you can make such a list. Suppose you believe you've enumerated all the real numbers between 0 and 1. Write them out. Maybe it looks like this. 1, 0.5132748. 2, 0.9174326. 3, 0.2314159. 4, 0.777819. And so on, going down forever. Each line has a real number between 0 and 1, written in its decimal expansion. And you're claiming that this list, if continued forever, would include every single real number between 0 and 1, every possible decimal. Cantor now does something brilliant. He constructs a new number, a specific real number between 0 and 1, that is guaranteed not to be anywhere on your list. Here's how. Look at the first digit after the decimal point in the first number on your list. In our example, it's 5. Now choose a different digit, any digit other than 5. Say you choose 6. That's the first digit of your new number. Now look at the second digit of the second number on your list. In our example, it's 1. Choose a different digit. Say you choose 2. That's the second digit of your new number. Look at the third digit of the third number. It's 1. Choose something else. Say you choose 2. That's the third digit. Keep going. For each number on your list, look at its nth digit, where n is its position in the list, and choose something different for the nth digit of your new number. You're going down the diagonal of this infinite list, changing each diagonal digit, constructing a new decimal. And here's the magic. This new number you've constructed is definitely a real number between 0 and 1. It's got an infinite string of digits after the decimal point. But it cannot be anywhere on your original list. How do we know? Because it differs from the first number on the list in at least the first digit. It differs from the second number in at least the second digit. It differs from the third number in at least the third digit. In general, it differs from the nth number on the list in at least the nth digit. So this new number is not the first number, not the second, not the third, not any number on your list. You said your list contained all real numbers between 0 and 1, but here's a real number that's not on the list. Your list was incomplete. And no matter how you rearrange the list, no matter how clever you are, you can always use this diagonal method to construct a number that's not on it. This means it's impossible to list all the real numbers. There is no one-to-one correspondence between the natural numbers and the real numbers. The real numbers are uncountable. They are a larger infinity than the natural numbers. Aleph null, the size of the naturals, is smaller than the size of the reals. We're calling the size of the reals C for continuum, though it's also sometimes written as 2 to the power of Aleph null, for reasons related to power sets that we'll explore a bit later. Let that sink in for a moment. 2 infinite sets, both endless, both going on forever, and yet one is provably larger than the other. Not just intuitively larger, not just bigger in some vague sense, but rigorously, mathematically, provably larger. You can demonstrate with logic that there are more real numbers than natural numbers, even though both are infinite. This was Cantor's great breakthrough. This was the moment when infinity stopped being one undifferentiated concept and became a landscape, a hierarchy, a structure with levels and distinctions. The diagonal argument is so elegant that it almost feels like magic. You start with an assumption that all the reals can be listed. You follow the logic of that assumption, constructing your list, and then you use the list itself to create something that can't be on the list. The assumption refutes itself. It's a proof by contradiction, and it's one of the most famous proofs in mathematics. When Cantor first published this result in the 1870s, it was shocking. People didn't want to believe it. Some mathematicians rejected it outright, saying it was nonsense, that infinity couldn't be divided into sizes. Others were intrigued but confused, unable to quite grasp what it meant. And a few, like Richard Dedekind and David Hilbert, saw the brilliance immediately and recognized that Cantor had opened a new door in mathematics, had revealed a whole new realm to explore. Think about what this means for a moment, before your thoughts drift away, before sleep takes you. It means the universe of numbers is richer than we thought. It means infinity is not a single thing, but a vast hierarchy of things, each larger than the last. It means that between the whole numbers, 1, 2, 3, there are not just fractions filling the gaps, but uncountably many real numbers, so many that you could never list them all even if you had forever to try. Every tiny interval on the number line, no matter how small, contains infinitely many rationals and uncountably infinitely many irrationals. The number line is crowded beyond imagining, dense beyond comprehension, and yet we can reason about it. We can prove things about it. We can say with certainty that there are more points on a line than counting numbers, even though both are infinite. Mathematics gives us this power, this ability to compare the incomparable, to measure the measureless. It's one of the reasons mathematics feels almost magical sometimes, why it inspires such awe, because it lets us think about things that are beyond direct experience, beyond physical reality, and yet still arrive at truths that are absolute and certain. Maybe your eyes are closed now. Maybe you're hovering in that space between waking and sleep, where thoughts blur together, where the boundaries of things soften. The diagonal argument might seem distant now, hard to hold on to. That's fine. You don't need to remember every step. Just the essence of it. Just the idea that Cantor showed with elegant logic that infinity comes in different sizes, that some infinite sets are bigger than others. That's the core of it. That's the discovery that changed everything. So we've established that there are at least 2 different sizes of infinity. Countable infinity, Aleph null, the size of the natural numbers. An uncountable infinity, C, the size of the real numbers, which is larger than Aleph null. But Cantor didn't stop there. He wanted to know, are there even larger infinities? Is there a hierarchy, a ladder of infinities climbing up and up without end? The answer, he discovered, was yes. There are infinitely many infinities, each one larger than the one before. And the key to understanding this comes from something called the power set. Let's talk about power sets for a moment. If you have a set, any set, the power set of that set is the collection of all its subsets, every possible subset, including the empty set, the set with nothing in it, and including the original set itself. For example, if your set is just the numbers 1 and 2, then the subsets are the empty set, the set containing just 1, the set containing just 2, and the set containing both 1 and 2. 4 subsets in total. So the power set has 4 elements. For a set with 3 elements, the power set has 8 elements. For 4 elements, 16. You might notice a pattern. If you have n elements, the power set has 2 to the power of n elements. That's where the notation 2 orgon comes from, and that's why the size of the continuum is sometimes written as 2r Aleph null, because the real numbers turn out to have the same cardinality as the power set of the natural numbers. But here's the key insight, the one that Cantor turned into a theorem. The power set of any set is always strictly larger than the original set. Always, even if the original set is infinite. This is called Cantor's theorem, and it's another application of the diagonal argument, adapted slightly, but using the same core logic. So if you take the natural numbers, which have size Aleph null, their power set is larger. Let's call that size Aleph 1. Then, if you take the power set of that, you get something even larger, Aleph 2. Take the power set again, Aleph 3. And you can keep going. Aleph 4, Aleph 5, Aleph 6, on and on. An infinite sequence of larger and larger infinities. And beyond the numbered alephs, there are limit points, like Aleph Omega, the size you reach by somehow collecting all the finite alephs together. And beyond that, even more. Let's pause here and really think about what this means. Each time you take a power set, you're creating all possible subsets of your previous set. And all possible subsets is a lot. For a finite set with n elements, the power set has 2n elements, which grows extraordinarily fast. A set with 3 elements has a power set with 8 elements. A set with 10 elements has a power set with 1024 elements. A set with just 64 elements has a power set with more than 18 quintillion elements. The power set operation is powerful indeed, and when you apply it to an infinite set, you jump to a strictly larger infinity. You don't just add a bit more, you leap to an entirely new level. The power set of the natural numbers is not just a little bigger than the natural numbers. It's uncountably larger. It's a fundamentally different size of infinity. And then you can do it again. The power set of the continuum is larger still, and again, each time reaching a new height, a new infinity that dwarfs all the ones below it. This means there's no biggest set. No matter what set you have, you can take its power set and get something strictly larger. There's no end to the hierarchy. It climbs forever. And this isn't speculation. This isn't philosophy. This is proven mathematics. Cantor's theorem establishes it with certainty. The hierarchy of infinities is real, rigorous, inescapable. You might wonder, is there a set of all sets? A universal set that contains absolutely everything? If there were such a set, you could take its power set. But the power set of the universal set would have to be larger than the universal set, which means it would have to contain sets that aren't in the universal set. But the universal set was supposed to contain everything. Contradiction. This is called Cantor's paradox, and it shows that the idea of a set of all sets leads to logical problems. In modern set theory, we avoid this by being careful about which collections we call sets. The collection of all sets is too big to be a set itself. It's what's called a proper class. It exists in some sense, but it's not a set, not an object you can treat like other mathematical objects. This is subtle, but it's important for keeping set theory consistent, for avoiding contradictions. These paradoxes caused a lot of worry in the early 20th century. Mathematicians realized that set theory, as Cantor had developed it, needed more careful foundations. You couldn't just define any collection you wanted and call it a set. You had to have axioms, rules that specified which sets you could construct and which operations you could perform. The resulting framework, Zermelo-Fraenkel, set theory with the axiom of choice, or ZFC, is what mathematicians use today. It's carefully constructed to avoid the paradoxes while still allowing all the useful mathematics that Cantor discovered. Within ZFC, the hierarchy of infinities is well defined. Aleph null, Aleph 1, Aleph 2, and so on, all exist as distinct cardinal numbers. You can prove theorems about them. You can compare them. You can do arithmetic with them, though the arithmetic is strange. Aleph null plus Aleph null equals Aleph null. Aleph null times Aleph null equals Aleph null. But 2 to the power of Aleph null is strictly larger, C, the continuum, and each Aleph has its own arithmetic, its own properties, its own place in the hierarchy. Mathematicians who work in set theory spend their careers exploring this hierarchy, proving theorems about large cardinals, studying the properties of different infinite sets, mapping out the landscape that Cantor first discovered. It's a rich field, full of deep and difficult problems, and it all started with Cantor's insight that infinity could be measured, compared, structured. That insight, controversial as it was, opened up a whole new branch of mathematics. Maybe you're barely following this now. Maybe the details are slipping away and you're just left with impressions. A tower of infinities, each one larger than the last. Going up forever. That's fine. That's the essence of it. The details can fade. The formulas can be forgotten. What matters is the sense of it. The idea that infinity is not one thing, but an endless hierarchy of things, each more infinite than the one before. That's what Cantor discovered. That's the landscape we've been wandering through tonight. This is the hierarchy of infinities that Cantor discovered. A tower that climbs upward without bound, each level representing a new kind of size, a new cardinality, larger than all the ones below it. It's a remarkable structure, almost dizzying in its implications. There's no largest infinity. No matter how far up the tower you go, you can always go higher. Take the power set. Go up another level. Let's pause and think about what this means. It means that infinity, which seems like it should be the ultimate concept, the end of bigness, is actually just the beginning. There are small infinities and large infinities and larger infinities and infinities so large they dwarf the ones that seemed large before. And the structure of this hierarchy is precise, mathematical, provable. It's not speculation or philosophy, it's rigorous mathematics. Cantor introduced a notation for these different infinities. He used the Hebrew letter Aleph, which looks like this, Bikhekem, and he put subscripts on it to denote different levels. Aleph null, 0, is the size of the natural numbers, the smallest infinite cardinal. Aleph 1, 1, is the next size up. Aleph 2, 2, is the next after that, and so on. Each Aleph represents a distinct infinite cardinality, a different size of infinity. The existence of these Aleph numbers was controversial when Cantor first proposed them. Mathematicians were uncomfortable with the idea that you could treat infinity as a number, even a special kind of number, and do arithmetic with it. But over time, as the rigorous foundations of set theory were developed, the Aleph numbers became accepted. They're now a standard part of mathematics, used in set theory, logic, topology, and other fields. One of the beautiful things about this hierarchy is that it shows how rich and structured the infinite can be. It's not chaos. It's not formless. There are patterns, relationships, levels. You can compare infinite sets and say definitively that one is larger than another. You can prove theorems about how these sizes interact, how they behave under various mathematical operations. The infinite becomes tractable, even though it remains, well, infinite. But there's a mystery here too, one that Cantor himself was never able to resolve. It's called the continuum hypothesis. Remember that we have Aleph null, the size of the natural numbers, and we have C, the size of the real numbers, the continuum. Cantor proved that C is larger than Aleph null. But the question is C equal to Aleph 1, the very next size up? Or is there some infinity in between? Some size that's bigger than the natural numbers, but smaller than the real numbers? Cantor believed that EC equals Aleph 1, that there's no intermediate size. But he couldn't prove it. He tried for years, thought he had a proof, then found a mistake. Thought he had a disproof, then found a mistake in that too. It tormented him, this question. It was one of the things that weighed on him during his periods of depression. The unanswered question, the problem he couldn't solve. In 1900, David Hilbert included the continuum hypothesis as the first problem on his famous list of 23 unsolved problems that he believed mathematics should focus on in the 20th century. He put it first because he thought it was fundamental, important, surely solvable with enough effort. But the continuum hypothesis turned out to be unlike any other problem on the list. In the 1930s, Kurt Gödel proved that the continuum hypothesis could not be disproved from the standard axioms of set theory, meaning if you assume the usual rules of mathematics, you can't prove that the continuum hypothesis is false. But that didn't mean it was true. It just meant you couldn't prove it false. Then, in the 1960s, Paul Cohen proved the other direction. He showed that the continuum hypothesis also couldn't be proved from the standard axioms. So you can't prove it true, and you can't prove it false. It's independent of the axioms. It's undecidable. What does that mean? It means that within the framework of standard mathematics, the continuum hypothesis is neither true nor false, or rather, you can choose to add it to your axioms as an additional assumption, and everything remains consistent. Or you can add its negation, assume it's false, and everything also remains consistent. The mathematics works either way. It's a choice, not a theorem. This was deeply troubling to many mathematicians. It suggested that there were fundamental questions about mathematics that mathematics itself couldn't answer. It challenged the idea that mathematical truth was absolute, that there was always a right answer waiting to be discovered. The continuum hypothesis remains unsolved in this strange sense. We know we can't solve it with current methods, and different mathematicians have different opinions about what that means, about whether it's a real question with a real answer that we just can't reach, or whether it's somehow not a well-defined question at all. But we're drifting into deep philosophical waters, and that's fine, because philosophy and mathematics blend together when you talk about infinity. The boundaries between what's mathematical, what's logical, what's metaphysical, they all get a bit fuzzy. And maybe that's appropriate. Maybe questions about the infinite are always going to be partly philosophical, partly mathematical, partly beyond our full grasp. You don't have to understand all the implications of the continuum hypothesis to appreciate what Cantor discovered. The key insight is simply this: there are different sizes of infinity. They form a hierarchy. Each level is larger than the one below. And this hierarchy is precise, provable, real, in a mathematical sense. That's the landscape Cantor revealed. That's the paradise Hilbert spoke of. Maybe you're drifting now, thoughts loosening, the details fading, but the sense of it remaining. A tower of infinities climbing upward forever. Aleph null, Aleph 1, Aleph 2, on and on. And somewhere in that tower, the continuum, the real numbers, occupying a place we can't quite pin down. It's beautiful and strange, and a little bit unsettling, the way the infinite often is. But it's also true. Provably, rigorously, mathematically true. We've touched on it already, but let's spend a little more time with the continuum hypothesis, because it's such a central question, such a fascinating puzzle, and because it shows something profound about the limits of mathematical knowledge. The continuum hypothesis, in its simplest form, is a question about the size of the real numbers. We know the real numbers form a larger infinity than the natural numbers. They're uncountable, while the naturals are countable. But exactly how much larger are they? Is the continuum the next size up after Aleph Null, or is there something in between? To put it more precisely, is the cardinality of the continuum equal to Aleph 1? Or is it some larger Aleph, like Aleph 2, or Aleph 17, or Aleph Omega? Cantor believed it was Aleph 1. He believed there was no set whose size was strictly between the size of the integers and the size of the reals. This belief, this conjecture, is the continuum hypothesis. Cantor worked on this problem for much of his life. He tried countless approaches. He thought he had proved it, then found errors in his reasoning. He thought he had disproved it, then found errors in that reasoning too. The problem resisted all his efforts. And it wasn't just Cantor. Other brilliant mathematicians took up the challenge over the decades that followed. None of them could crack it. In 1900, as we mentioned, Hilbert made the continuum hypothesis the first problem on his list. He was optimistic. He thought mathematics was on the verge of solving all its major problems. He thought that with enough work, enough clever insights, everything could be proved or disproved. The continuum hypothesis seemed like a hard problem, but not an impossible one. Surely someone would solve it eventually. What Hilbert didn't anticipate, what nobody anticipated at the time, was that some mathematical questions might be unsolvable in principle, not just difficult in practice. The idea that there could be statements that were neither provable nor disprovable from the axioms of mathematics, that was a radical notion. It challenged the very foundations of what mathematics was supposed to be. But then Kurt Gödel came along, and everything changed. Gödel was working on mathematical logic, on questions about the foundations of mathematics, about what could and couldn't be proved. In 1931, he published his incompleteness theorems, which showed that in any sufficiently powerful mathematical system, there would always be true statements that couldn't be proved within that system. Mathematics, in other words, was fundamentally incomplete. There would always be truths beyond the reach of proof. This was a shocking result, a paradigm shift in how mathematicians thought about their field, and it had implications for the continuum hypothesis. If there were unprovable truths, could the continuum hypothesis be one of them? In 1940, Gödel turned his attention specifically to the continuum hypothesis. He constructed a special model of set theory called the constructible universe, and he showed that within this model, the continuum hypothesis was true. More importantly, he showed that if the standard axioms of set theory were consistent, then adding the continuum hypothesis as an additional axiom would not create any contradictions. In other words, the continuum hypothesis was consistent with the axioms. You could assume it was true, and everything would work out fine mathematically. But Gödel's result was only half the story. He had shown that the continuum hypothesis couldn't be disproved, but could it be proved? For more than 20 years, that question remained open. And then, in 1963, a young mathematician named Paul Cohen made a breakthrough. He developed a new technique called forcing, a way of constructing models of set theory with very specific properties. And using this technique, he showed that you could also build a model where the continuum hypothesis was false, where there were infinities strictly between Aleph null and the continuum. Cohen's result completed the picture. The continuum hypothesis could neither be proved nor disproved from the standard axioms of set theory. It was independent. It was undecidable. You could consistently assume it was true, or consistently assume it was false. Mathematics didn't care which choice you made. Both versions of mathematics were valid, consistent, equally legitimate. This was a profound and troubling result. It meant that one of the most natural questions you could ask about infinite sets didn't have a definitive answer. The size of the continuum was, in a sense, left open by mathematics. It could be Aleph 1, or it could be something larger, depending on which additional assumptions you made beyond the standard axioms. Different mathematicians have reacted to this result in different ways. Some, like Gödel himself, believed that the continuum hypothesis did have a definite truth value, that our current axioms were simply too weak to determine it, and that we needed to find new, more powerful axioms that would settle the question. They saw the independence result not as the end of the story, but as a sign that we needed to dig deeper, to find the right framework in which the question could be answered. Others took a more pluralistic view. They said that perhaps there was no single, correct answer to the continuum hypothesis. Perhaps there were different, equally valid versions of set theory, some where it was true and some where it was false, and mathematics was richer for having this multiplicity of possibilities. The universe of sets, on this view, was not a single fixed structure, but a multiverse of structures, each internally consistent, each reflecting different choices about how to extend the basic axioms, and still others took a more deflationary view. They suggested that perhaps the continuum hypothesis was simply not a well-defined question. Perhaps it was asking about something that didn't have a determinate answer, like asking whether the number 5 is married. The question has the form of a question, but it's not actually answerable because it's not about anything real. On this view, the independence result showed that the continuum hypothesis was pseudo-question, something that looked like mathematics, but wasn't really. These are deep philosophical disagreements, and they're still being debated today, more than 60 years after Cohen's proof. The continuum hypothesis remains one of the great mysteries of mathematics, not because we don't know enough, but because we know too much. We know it can't be settled by the methods we have. We know that standard mathematics leaves it open, and we're still grappling with what that means, with how to think about mathematical truth when faced with such radical undecidability. For our purposes tonight, as we drift through these ideas on our way to sleep, the key thing to understand is simply this. The continuum hypothesis was a question Cantor asked, a question about the size of the real numbers, and it turned out to be unanswerable in a surprising way. Not unanswerable because it was too hard, but unanswerable because mathematics itself, as currently formulated, doesn't determine the answer. It's a question on the edge of what mathematics can do, a place where logic meets mystery, where proof meets uncertainty. And maybe that's fitting. Maybe questions about infinity should be like that, should take us to the boundaries of knowledge, should show us the limits of even our most powerful tools. Infinity is, after all, beyond the finite, beyond what we can fully grasp, fully enumerate, fully capture in symbols and proofs. Cantor brought mathematics as far as it could go into the realm of the infinite. He built a rigorous theory, proved stunning theorems, revealed a hierarchy we didn't know existed. But even his work, brilliant as it was, couldn't answer everything. Some questions remain, some mysteries endure, and that's okay. Mathematics doesn't have to answer everything to be beautiful, to be valuable, to be worth exploring. Sometimes the questions themselves are enough. Sometimes just knowing what can and can't be known is a kind of wisdom. Maybe you're barely awake now, just fragments of thoughts drifting by. The continuum hypothesis, a question without an answer. Infinity, larger than itself. Cantor, asking questions nobody had asked. It's all blurring together, becoming dreamlike, which is exactly as it should be. Let it go. Let the mathematics fade into the background, into the soft darkness behind your closed eyes. It will still be there tomorrow, patient and eternal. It's been there for billions of years, in the structure of numbers, in the patterns of the universe. It can wait while you sleep. As we move toward the close of our gentle journey through infinity, let's step back for a moment and think about what all of this means, not just mathematically, but philosophically, humanly. What does it mean that infinity comes in different sizes? What does it tell us about mathematics, about reality, about the strange capacity of the human mind to reason about things beyond experience? One thing it shows is that mathematics is not simply a practical tool for counting and measuring. Yes, mathematics is useful. It helps us build bridges, predict weather, design computers, cure diseases. But mathematics is also something else, something deeper. It's a way of exploring pure patterns, pure structures, pure relationships that exist in some abstract realm beyond the physical world. The hierarchy of infinities that Cantor discovered. It doesn't exist anywhere in space and time. You won't find it under a rock or see it through a telescope. And yet it's real, in the sense that it's true. The theorems about different sizes of infinity are not matters of opinion. They're provable, rigorous, certain. This suggests something profound about the nature of mathematical truth. Mathematical objects, like numbers and sets and infinities, they exist in a peculiar way. They're not physical, but they're not arbitrary either. They have properties, behaviors, relationships that we discover rather than invent. When Cantor proved that the real numbers are uncountable, he wasn't just making up a definition. He was uncovering a fact about the structure of the mathematical universe, a fact that was true before he proved it and would remain true even if he'd never existed. This is sometimes called mathematical Platonism, after the ancient philosopher Plato, who believed in a realm of perfect, eternal forms that existed beyond the messy, changing world of physical objects. Mathematical Platonists believe that numbers and mathematical structures inhabit a similar realm. They're discovered, not created. They're objective, not subjective. And the job of the mathematician is to explore this realm, to map it out, to prove theorems that describe its structure. Not all mathematicians are Platonists. Some take a more nominalist view, saying that mathematical objects are just useful fictions, concepts we invent to help us organize our thinking, but which don't have any independent existence. On this view, when Cantor proved his theorems about infinity, he was creating a framework, building a structure, not discovering something that was already there. And there are many positions in between these extremes. Some mathematicians are formalists, focusing on mathematics as a game played with symbols according to rules, without worrying too much about what, if anything, the symbols mean. Others are intuitionists or constructivists, believing that mathematical objects only exist if we can construct them, if we can give explicit procedures for building them or calculating with them. These philosophical debates are old and probably unresolvable. Different mathematicians work with different implicit philosophies, and often those differences don't matter much for day-to-day mathematical practice. You can prove theorems without agreeing on the ultimate nature of mathematical reality. The proofs work either way. But when you think about infinity, these questions become harder to ignore, because infinity is so far removed from ordinary experience. We encounter finite things all the time. We can count them, measure them, compare them. But we never encounter an actually infinite collection of objects. We never finish counting to infinity. So when we reason about infinite sets, when we prove that some infinities are larger than others, what exactly are we talking about? Are we describing a real structure that exists somewhere? Or are we just playing a very sophisticated game with symbols and rules? Cantor himself was deeply religious. He saw his mathematics as a way of approaching the divine. He believed that God was infinite in a way that transcended even the mathematical infinities he had discovered. The Aleph numbers, no matter how far up the hierarchy you went, were still what he called transfinite, beyond the finite, but not truly infinite, in the absolute sense that God was infinite. For Cantor, mathematics and theology were intertwined. His work on infinity was, in part, an attempt to understand something about the nature of God. Not everyone shares that view, of course. Many mathematicians are secular, and they find beauty and meaning in mathematics without any religious framework. But it's interesting to note that the questions infinity raises, they're not just mathematical questions. They're also metaphysical, touching on issues of existence, reality, truth, meaning. Another philosophical issue that arises with infinity is the nature of mathematical knowledge. How do we know things about infinity? We can't observe it. We can't experiment with it. We can't build an infinite collection of objects and study them empirically. All we have is reason, logic, proof. We start with axioms, statements we take as given, and we derive consequences from them using the rules of logic. And through this process, we come to know things about infinity with absolute certainty, even though we've never encountered infinity in any direct way. This is remarkable when you think about it. It means that the human mind is capable of grasping truths about things that are entirely beyond human experience. We're finite creatures, living finite lives, thinking finite thoughts, and yet we can reason about the infinite. We can prove theorems about it. We can build a rigorous, coherent theory that describes its structure. That's a testament to the power of abstract thought, to the capacity of reason to transcend the boundaries of the sensory world. Of course, there are limits to this power. As the continuum hypothesis shows, there are questions about infinity that our current mathematical framework can't answer. There are mysteries that resist even the most powerful logical tools we have. And maybe that's a good thing. Maybe it's healthy to be reminded that there are limits to knowledge, that not everything can be captured in symbols and proofs, that mystery has a place even in mathematics, the most rational of disciplines. Cantor's work on infinity also raises questions about mathematical creativity and discovery. Was Cantor a genius because he invented a new way of thinking about infinity, or because he discovered truths about infinity that were already there, waiting to be found? The answer probably depends on your philosophy of mathematics. But either way, there's no denying that Cantor did something extraordinary. He asked questions nobody had asked before. He developed concepts nobody had thought of. He proved theorems that changed the landscape of mathematics forever, and he paid a price for it. His ideas were rejected, ridiculed, attacked. He suffered mental illness, depression, periods of hospitalization. He died in relative obscurity, his work still controversial, his final years shadowed by war and illness and isolation. It's a sobering reminder that intellectual breakthroughs often come with personal costs, that seeing things differently from everyone else can be lonely and difficult and painful. But his work endured. His ideas, once controversial, became foundational. The paradise he created, as Hilbert called it, became a central part of modern mathematics. Today, every student who studies set theory learns about Cantor's hierarchy of infinities. His theorems are in textbooks. His concepts are used in research. His name is remembered with honor as one of the great mathematical minds of the 19th century. There's a lesson in that, maybe. That truth has a way of persisting, even when it's initially rejected. The good ideas eventually find acceptance, even if it takes time. That the work matters, even if the person doing the work suffers for it. It's not a comforting lesson, necessarily. We'd prefer to live in a world where brilliant people are recognized and celebrated during their lifetimes, where doing good work brings happiness and success. But history shows that's not always how it goes. Sometimes the recognition comes later. Sometimes the happiness never comes at all. And yet the work still matters. The truth still matters. The ideas still change the world. As we drift toward the end of our exploration of infinity, maybe that's what we're left with, a sense of the vastness and strangeness of the mathematical universe, a sense of the human capacity to reason about things beyond experience, a sense of the beauty and difficulty of asking deep questions, of pushing at the boundaries of knowledge, and a sense, perhaps, of gratitude toward the people like Georg Cantor who asked those questions, who pushed those boundaries, who gave us new ways of seeing, even at great personal cost. You're probably very drowsy now, if you're still awake at all. The ideas are becoming distant, abstract, like shapes seen through fog. That's perfect. That's the point. Mathematics, especially mathematics about infinity, is a vast landscape, and tonight we've walked through just a small part of it. We've seen that infinity is not one thing, but many things, that it has structure and hierarchy, that some infinities are provably larger than others. We've met Georg Cantor, the man who discovered this, and felt something of his struggle. we've glimpsed the philosophical questions that infinity raises, questions about reality and knowledge and truth. But you don't have to carry all of this into sleep. You don't have to remember the proofs or the definitions or the philosophical positions. Just the essence of it, if anything. Just the sense that infinity is richer and stranger than you might have thought, that mathematics can be beautiful and profound, that the human mind is capable of extraordinary things, that there are questions worth asking even when they're hard, even when the answers are elusive, even when asking them comes at a cost. The mathematics will still be there in the morning, patient and eternal. The infinities will still stretch upward in their hierarchy, aleph after aleph, without end. The continuum hypothesis will still be undecidable, a question at the edge of knowledge. And somewhere in the history of thought, Georg Cantor will still be remembered, a man who saw further than others, who dared to measure the infinite, who created a paradise from which, as Hilbert said, we will never be expelled. And now, as our journey through the landscapes of infinity comes to a quiet close, maybe you're still here, still listening, or maybe you've already drifted away to somewhere softer and deeper. Either way is exactly right. These ideas about infinity, about endless things, and how some endlessness can be larger than other endlessness, they'll wait. They've been waiting for more than a century. They can wait through the night while you sleep. We've wandered together through strange territory tonight. We started with a question that sounds impossible, a question that seems to contradict itself. Can infinity be bigger than infinity? And we found, slowly, gently, that the answer is yes. That Georg Cantor, a troubled, brilliant man in the late 1800s, proved this rigorously, that there are countable infinities and uncountable infinities, aleph null and the continuum, and beyond them, an entire tower of larger and larger infinities climbing upward without bound. We saw Hilbert's Hotel, where infinity plus one still equals infinity, where full can always accommodate more, because there's no last room, no final space. We trace the diagonal argument, that elegant proof that shows the real numbers resist any attempt to list them all, that they're fundamentally larger than the counting numbers. We touched on the continuum hypothesis, that beautiful unanswered question about exactly how much larger the real numbers are, a question that turned out to be undecidable, beyond the reach of proof. And maybe, in all of this, you felt something of the strangeness and beauty of mathematics, how it can take concepts that seem like pure abstraction, like infinity, and build rigorous theories around them, how it can prove things with absolute certainty about objects we can never see or touch, how it can reveal structures and patterns that were hidden, waiting, until someone had the courage and insight to ask the right questions. Georg Cantor asked those questions. He paid a price for it, faced ridicule and rejection, struggled with mental illness, died in obscurity and pain. But his ideas survived him. His mathematics became fundamental, the paradise he created real. And tonight, more than 100 years after his death, we're still talking about his discoveries, still marveling at what he found when he looked into the infinite. There's something poetic about that, about how ideas outlast the people who have them, about how truth persists even when it's initially rejected, about how the work of the mind, the work of reason and imagination and courage, creates something that endures beyond any individual life. You're lying there now. your body heavy against the mattress, your breathing slow and deep. The room around you is quiet, or maybe there are small sounds, the hum of machines, the whisper of wind, the distant murmur of the world going on without you. And inside you, your own infinity is at work. The infinite complexity of your cells, your neurons firing in patterns too intricate to ever fully map, the infinite divisibility of moments, each second containing within its smaller and smaller slices of time. The infinite capacity of consciousness to reflect on itself, to think about thinking, to wonder about wondering. In some small way, you're part of the infinite too, made of atoms that follow mathematical laws, living in a universe that may or may not be infinite in space, in time, in possibility, capable of thoughts about infinity, about endless things, about questions that reach beyond experience. Cantor showed that infinity has structure, has levels, has distinctions. But he also showed that infinity will always have mysteries, will always exceed our full understanding, will always leave some questions unanswered. And maybe that's comforting, in a strange way, that there's always more to know, more to discover, more to wonder about, that the universe, mathematical or physical or mental, is not exhausted, that there are questions for future generations to ask, puzzles for curious minds to explore, mysteries that will keep calling to people who want to understand. Tonight, we've explored one tiny corner of that vast landscape of knowledge. We've asked whether infinity can be bigger than itself, and we've found that yes, some infinities are larger than others, that the endless comes in different sizes. We've met the man who discovered this, and we've felt something of the price he paid for his vision. And now, as sleep draws near, or has already arrived, we can rest knowing that these ideas are safe, preserved, waiting for anyone who wants to explore them further. If you're still awake, if you've made it all the way through this gentle journey through infinite things, thank you for your attention, for your patience, for your willingness to think about mathematics as a way to ease towards sleep rather than as something stressful or demanding. If these quiet explorations of numbers and patterns and endless hierarchies help you wind down at night, if they give your mind something calm to settle on as you drift away, consider subscribing to Math for Sleep. It helps others find their way here too, one person at a time, looking for rest and curiosity in equal measure. Sleep well, dream if you dream, and let the mathematics be what it is: patterns in the mind, structures in the abstract realm, truths waiting patiently whether we think about them or not. The infinities will still be there tomorrow, Aleph Null, and the continuum, and all the larger Alephs beyond. The continuum hypothesis will still be undecidable. Georg Cantor will still be remembered, a man who saw what others couldn't see. And somewhere in the quiet of your rest, maybe a fragment of this will remain, a whisper of the idea that infinity is stranger and richer than we ever imagined. Good night.